Hello. It's such a dramatic shift from the chill music to pointers. We should play death marching music now. We should play... I don't know what to play. Something... No, I'm kidding. I'm kidding, everyone. It's not that bad. Hello. I'm going to hide that. That's annoying. All right. Audio check is good. The bars are matched. That looks good. Put that away. I have a glass of water. Who listened to me? Who came to the lecture? How many of you are there? 80. That's not very good. All right. Well, screw the others that aren't here. Hello, everyone. You came in person. We told you not to. Be careful. It's apparently really... I mean, it's not too bad right now where I am, but it's looking pretty grim. So everyone stay safe. Okay, we should get straight into it. Let's go to the slides. Oh, that's rough that you had an exam. All right, we're talking about pointers right now. It's almost as if we forecasted it. Okay. I saw a guy in Reels who looks like you. I can promise you that wasn't me. That's all I can promise you. Where's my slides? Here. All right. Okay. Apparently a reminder to check help sessions and revision sessions. I'm not going to talk too much about that. Let's talk about pointers. We want to get straight into it, I think. Okay, who's been told that pointers are really scary? I mean, I'm guilty of this. I was kind of talking about them yesterday. Pointers are one of the topics that really make C quite a different language to teach than other languages. Yeah, I know, I told you that was scary. But that was just because I'm trying to scare you to come to the lecture, which apparently didn't really work. But most of you will watch it online later. Okay, so I want everyone to sort of shake all their negative preconceptions off. Pointers really aren't that bad, and you're lucky you've got a great lecturer who's going to make them really simple, yeah? So that's what we're going to do today. All right. Let me move this here, move this here. That looks a bit better. Yeah, I'm really humble. That's good. Okay, so let's take a step back and talk about memory, right? We've spoken about memory a lot. Memory is the way we store data in short-term memory of a program, of a computer. When we create variables in C or in any programming language, really, what we're really doing is requesting the operating system to allocate us a piece of memory, a piece of RAM, that we can use for the life cycle of a program or of a variable. So we have an integer, we call an integer x. What we're really doing is asking the operating system for 32 bits of storage to store the zeros and ones required to represent an integer, okay? And the way I think about memory is as a big grid. A big grid, and each segment has a unique identifier. This is really important. So let's have a look at this. So I might make this a bit bigger, which is probably going to screw up that. So let me do that. Apologies, I just wanted to see it myself a bit clearer. Okay, so here is a grid. There's a couple typos here, but it doesn't really matter. So in this example, every chunk of the grid is 32 bits wide, so we can store 32 zeros and ones in that memory. So there's 32 transistors, basically. And if you see here, every element has an address. Now, this is not something we've really spoken about much, but this is kind of logical if you think about it, because we need to be able to access different pieces of memory to store different values. Okay, so in this piece of memory, right, we have the integer 53 is being stored. I don't know if you can see this very well. It's a little bit small. In this piece of memory, we have the character A, right? That also fits. And you can see that this memory address, like I've just sort of made them up here, but it's a different memory address to this one. And this one's got a memory address of 2. It's the next address over. And this one is storing a double, a floating point with 0.35. Then you might have some chunks of unallocated memory. They've all got addresses, right? But we're just not talking about them. And then down here, what are we storing? Who can tell me what this is? I can't really select it, but we have 4 memory addresses. But what is that really storing? Why don't we do that? I should check. Yeah, it's a string. It's exactly right. It's an array. And an array is, sequence of elements right next to each other because it's contiguous. And they're all storing characters. But really what I've done here, or tried to do here, is to store a string. So we have the 19th memory address is storing the character J, the 20th A, the 21st K, and the 21st E. All right, so what I'm trying to say here is that we've spoken about, we know this, right? We can store data in chunks of memory. But what I'm really trying to say is that we have an address associated with each element. And while I wanted to bring up, what did I use to make this diagram now? Can't remember. Anyway, I'll think about that later. So this is like an overview of memory. But so far, okay, we've only been dealing with values. And so what I mean by that is, we don't deal with addresses ourselves in our program, right? So like this should be pretty obvious. If I jump back to my code, oh, why did that do that? There we go. If I jump back to my code and I just go back to a program that we wrote the other day, let's have a look at maybe nothing too bad. Okay, let's just look at this, right? When I have this int I here, create an integer in memory called I, right? The operating system goes off, requests the memory, and gives it to us. Oh, these comments are annoying. We don't deal with any addresses. Okay? Is everything I've said making sense so far? So I just want to show you that without dealing with addresses, we can create a variable and store things in the variable, store values in the variable. And now I've got a question for you. This is an important question, right? How do I refer back to the variable at the moment? Just type it in the chat. How do I refer back? Like, I've gone off, I've created some memory. Yeah, exactly right. You're like, the lecture delay is really good today. I get the identifier I. This I get given. I'm actually creating it. So I'm using this identifier. We use our identifier in code to refer back. All right. So we're all agreed. We're all happy. This is how we deal with memory and variables at the moment. Okay? Fantastic. Go back to the slides. So that's how we've been doing things at the moment. But there's another way of doing things. We can not just access the value at I, we can access the address. And all we're doing here, don't let it get too scary, all we're doing is we're saying that if every element has a value, it also has an address, and we can read the address, and we can do things to the address. Okay. Let's do a bit of a metaphor. You all live, or hope, okay. You all live in a building, usually. Maybe not everyone actually does, but we hope that they do. You live in a building on a street, or a house, or an apartment, or whatever it is. You have this identifier called like your house or your home that you go back to. You're going home. If you tell people, I'm going home, you're like, yeah, I'm going home. You get on the train and you go home. And you walk into your street, and then you walk into your front door, and you're home, right? But your home has an address. And you map your identifier home to that address. And so the address is like, number 1, whatever it is, whatever the name of the street is, George Street, Sydney. That would be nice to live there. So that's like the address, and your home is like, and your variable is like the house, and you can put stuff in the house. But sometimes it makes sense that you want to give people that address, because sometimes people you can't just say, hey, can you post me this parcel to my home? They're going to say, what? Like, I don't know where you live. I need your address. Sometimes we need to know the address, and there's lots of things we can do once we know the address. Before I actually continue on my slides, I want to go back to my code and show you a few little things about that. So let's do this. I say int I is equal to the integer, the value 50. Well, welcome, Dylan. You're in for the show now. I hope you're ready to learn about pointers. Int I is equal to the value 50. I can printf %d \n. I is, that's not what I want to do. I is 50 \n, and I give it I. All right, nothing new here, I hope. So we compile this. This is called pointers intro out to program. We run program, and we get I is 50. All right. What we can also do is print the memory address, and we can just use this ampersand is stored at, pretty sure that's right. It's been a little while since I did this. Yes, no errors. That's good. Okay, cool. Every variable, this is the key that you need to understand. Every variable has an address. Because what is a variable? It's just a piece of memory. And so all memory is located, in that grid, in these streets, and every location, every addressable location has an address. This is the real memory address of where my operating system on my computer placed this variable, this I variable that I asked it to create. Okay? If you run this program, which I urge you to do, you run this program, you will get a different value. Okay? Why will you get a different value? Because your computer and your operating system is different, and you've got a different arrangement of memory, you've got different amount of memory, you've got different programs running, all using different amounts of memory. And so the memory that your operating system can carve out for you is just naturally going to be in a different place. So you'll typically see a different value here. In fact, if I turned my computer off, reran this program, I would get a different value here. It's dynamic. So this is the location of where that I variable is being stored. Okay? Shrek's official account. Is this why we use the ampersand in scanf? Yes. A few things are going to make sense now that we haven't really been able to talk about. So we print an address with %p. P stands for pointer. The ampersand I means address of variable that follows. Okay, so that's really important. So we're just saying, hey, I don't want you to print the value I want you to print the address. So all that's key to understand here is that in C, when you use a variable to a variable's identifier, it automatically goes and fetches the value. Because that's the most useful thing to do by default, but we can also get the address. All right, if I just pause for a second here, do we have any questions about what I've covered so far? Dylan says, if you free the variable, delete it, would that create a problem? We'll talk about that later. I don't want to talk about that just yet. But you can't free a variable created like this anyway. Do pointers change the variable globally if this was used in a function? Yes, this is one of the big things that change with pointers animation. So that's a good pickup. That's true. We'll talk more about that too, though. I'm not going to go too much detail. So is that why with scanf we use the ampersand? Because we're saying print the value at this memory address. So scanf, we're not saying print the value. We're saying I want to store. So the way scanf works, and we will talk about this later, but scanf says, hey, take a value from the standard input and place it into this memory address. So it actually gets given a memory address. And so because you were giving it a memory address, we need to get the address of the variable that we really want to store it into. So accessing the address is called a pointer? No. My next slide is what is a pointer. So this is not a point. This is not really a pointer. This is just a memory address. Is the %p the same for all data types? Fantastic question. And the answer is yes. So memory addresses are always printed with %p. It doesn't matter if this was an integer, a character, a double, a struct, right? That would always be, the memory address is always a memory address, is always %p. Oh my God, lots of questions today. Do I have to write down void star ampersand I when I want to print the address? No, you don't have to. You don't have, that's casting it to a void pointer, which we actually don't want you to do in this course. That's actually against the style guide. A pointer as a pointer, we're not there yet, but good question. So scanf is only reading but storing. That's correct. It reads and then stores, but it's not printing. So it reads data from standard input and it needs a memory address to place that value in. All right, I think you guys are asking good questions, which means you're on the right track. Okay, this is the key. So someone asked what a pointer actually is. You can't see my slides. Someone asked what a pointer actually is. This is the key. A pointer is a variable, a new variable type, okay, wherein we don't store a value, we store an address. We store a memory address, and I can hear the storm really kicking up. So it's if I wanted to, so the question is, if I want to store this memory address, what would the data type be? That's a pointer. All right. So you can't see what I'm code. If I wanted to store this memory address in variable, so in memory, I want the address and then like I'm storing in memory an address. So it'd be address. Okay, that's what a pointer is. Does that make sense? So are pointers to pointers useful? Sometimes they are. Yes, absolutely. Again, we'll be talking a lot more about this stuff. And I'm just cautious to get too far ahead of like today's content. So I don't want to get off track with future stuff, but it's all coming. Okay, so let's look at this slide, the pointer syntax. So what does it mean to create a pointer? Well, what it means is I want to store a piece of, I want to store a memory address in memory. And the way we do this is really similar to the way we create a variable of any type. So we still provide the type of the value that we will be pointing to by the address. We still give it a name because it's just a variable. Pointers are just variables. And the only difference is this little asterisk before the variable name and after the type. And so what this means is, hey, I don't want to store, right, an integer or a double or a character or a struct or an enum. I want to store a pointer to that data type. So the asterisk is the second artifact that we're introducing today. The first is the ampersand. If we jump back to code, let's go back to code. Here's what I'm going to do for you guys. I'm going to make like a cheat sheet. Pointers, cheat sheet. I'll make it a C program. So we've got the ampersand. When placed before a variable, this means address of. Do I need to elaborate on that? That's probably okay. So we get the asterisk now. When placed before, or it's actually after a type in a new variable declaration, it means create a pointer. Okay, so I'm going to make this little cheat sheet that you can refer back to, and we're going to grow this cheat sheet as the lecture goes, because there are a few other things that will change. That we'll need to add to this. Cool. All right. So this is the syntax. So the asterisk means don't request storage. Yeah. Okay. Good. So let's have a look at an example. You can see it looks really similar to the way we just create an integer. We give it the data type, we give it the name of the variable. In this case, I just called it pointer. Maybe that's a bad name. I might actually, oh no, don't worry about it. And this means I want a reference to a pointer. Here, right, I'm doing the same thing, but with a struct, so a more complex data type. So I've got this student struct, so I create a student struct just as I always would. I've called it student, but there's this asterisk here, which means it's a pointer to a student. It's not storing a student. So I want to quiz you guys. To see how you're going so far. So go back to my code. All right, so let's say I've got int x equals 5. Let's say I've got, let's say I have double y equals 5.5, 5.6. Then let's say I've got struct student int age double wham, and I have struct student, don't forget the semicolon, struct student, my student, can I do this? I can do 25 and then 4.88.3. I can do that, right? All right. So I want to ask you all a question. How many bits / bytes for each is being stored? So I'll give you all a second to figure this out. So that's right, 32 bits for integer x. It's 32 bits, not bytes. 8 bytes. That would be quite big. So 32 bits here. Is it 4? Wait, is it 4 bytes or 8 bytes? Chat, help me. See how many bytes for an int. Oh, it's 4 bytes. Is that right? It's 4 bytes. Never mind. It's 4 bytes. It's 4 bytes. Yeah, and 8 bytes for a double. Okay, so this is 4 bytes, 32 bits. It's 32 times 8. Obviously, there's 8 bits in a byte. So double is going to be 8 bytes, 64 bits. You cannot have less than a bit. That's correct. And then what will this one be? Student uses 12 bytes. Yeah, we just add 8 plus 12. So 12 bytes, 64 plus 32 is 96 bits. Yeah, so many of you got this. That's great. All right, so now why is this the case? Because we need enough memory to store this data type's size. Let me show you something cool. there is this size of function in C that you can use to tell you the size of a data type. The reason this is important is because you shouldn't really memorize the size of a data type because it can actually change. I just compiled the wrong program. It can actually change depending on the different environment. Let's not worry about those warnings. So here we get this. This is in bytes. So it tells us, let me recompile this. It tells us that on my environment, an integer is 4 bytes, okay? I think we should even be able to do this. And we get 16. Okay, that's interesting. And don't kill me for it not being 12. I can't explain why that is not 12. My point actually is that you shouldn't, we shouldn't rely too much on calculating the size, especially of structs. We should trust the computer to tell us the size of things. But the point I'm trying to make here, and that shouldn't be int there in that case, but the point I'm trying to make here is that we can actually check the size of an int each time. So we can like prove it. So we can do this. And you know, the other thing you can actually do is you can just give it the variable itself. I'm pretty sure. Yeah, the size of x is 4. So you can give it a variable as well, and it will tell you. Put \n. So I'm going to do this. I want to do y. And here we want to do struct my student. All right. Cool. And so we get that printed out. So we can check the size required to store particular data types in particular variables. Let me quickly look at chat. So isn't that malloc? No, we're not touching malloc today at all. Is knowing the amount of bytes and bits for different data types essential? Yeah, it's not essential to memorize them. In fact, you should not memorize them because this is where people get into problems, because this is the size of the data types on my computer. If you went to an older computer or a different computer on a different version of C on a different operating system, you may get different values. Probably not for an integer. Integers are pretty always 32 bits, but you can't guarantee the size. So you should use these tools to check the size dynamically. Oh, we use sizeof in malloc. Yes, we do that. But sizeof is just a function that tells us the size of a data type. Okay, all right. Why am I talking about this? Because the real thing I wanted to teach you all is to say that we can also check the size of a pointer to a data type. So if I say double yptr is a pointer, okay? The size of y underscore ptr is going to be the size of yptr, and that's still going to be in bits. So the size of y pointer is 8 bytes. And what you'll see, which is really interesting, is that it's always 8 bytes, right? So if I do the same thing here, well, it's not, I guess it's not too interesting. We'll see that the x pointer is also 8 bytes. The y pointer is also 8 bytes. So why are the pointers 8 bytes? Well, I'm on a 64-bit machine. And what that means is my memory is addressable in increments of 64 bits. So 64 bits is 8 bytes. So that's the size, that's the minimum size of an address on my machine. Again, this could be different on your machine, right? So if you're on a 32-bit computer, your pointers will be in 32-bit increments. On my computer, they're 64 bits. So the minimum addressable space is a 64-bit pointer. Now this is why our struct here is 16 bytes, because we actually can't always, if something is an odd number of bits or bytes, like let's say something is 3 bits and I've got 2 of them, but my pointers can only increment in 64 bits, I won't be able to actually reach stuff. So we actually have to pack memory, and this is why we actually make some structs bigger so that they always fit in a 64-bit addressable memory. Does that make sense? So that's why the struct is 16 bytes. It's because on my computer, my pointers can only increment in 8 bytes. So everything has to be divisible by 8. Okay? Anyone having an aha moment? Yeah, don't worry about this. Don't worry about those warnings. You can just ignore them for this sake. What address is the int asterisk x point address accessing? We don't know. My point is just to show us how large it is. We don't actually care. We're not using it here. It's rounding to the nearest multiple of 8. That's exactly right. Why is it doing that? Because otherwise it wouldn't be able to reach it. It's just like you've got a street. Let's do this. It's just like you've got a street of houses, and what you're saying is like, oh, I need like I want to put, and house numbers can only go up by integers, like, you know, house number 1, house number 2, house number 3. And I'm saying like I want to address like my shed that sits between the 2 houses. You can't. What do you write on the envelope? Like 1.5. You know, that doesn't mean anything. So you can't put something there. You have to move it over, right? And so, but it's all taken care of for you. So it just makes the struct bigger so that the next piece of memory will be divisible by 8 bytes. Does that make sense, guys? It's all memory. Programming is all memory. It's all about putting data in memory. It's really cool. Okay, let me look at this chat. So if you're on a 32-bit machine, would the struct size be 12 bytes? Yeah, if you're on a 32-bit machine, things would be different. You might, in this case, would you have been able to fit it? I think you would have. Yeah, that's right. So that's right, Shrek. Is it important for us to know the size of pointers variables? Is there any specific reason at our level why we would need to? Yeah, Thomas, this is really important because this is the foundation of programming. Programming is putting data in memory and retrieving it later and manipulating it. And in fact, you'll see the more and more we talk why this stuff becomes important. Now, again, you do not need to memorize the data types and how much memory they require. In fact, don't memorize it in a way because you don't get much value out of it. It's good to know roughly, like an integer is smaller than a double, of course, but when you move on, when you write code, it will run in different environments that might work differently. So you want to use these tools, but you want to know the fundamental concepts. You don't need to memorize stuff. Okay, so does that mean our program functions we're going to be able to edit variables across the program by pointing to the memory address? Yes and no, Alien. So yes, you will be able to manipulate things outside of the function. Like, no doesn't mean that like you're just getting global variables all of a sudden. Like, it's much more controlled than that. Then how come that can only apply to structs? Like, why can an integer be 4 bytes? An integer, because a 4-byte integer is still divisible. I see what you're saying, I think. I will send you a link to read up about it. And it will answer for you. Let's see here. Here's a good article if you want to read more about this. It's complicated is also the answer. Oh, USID asks a great question. How do pointers relate to the connect, for example, yesterday, where the array in the function didn't have to be returned? Let's save that for later, but great spot and good question. Very good. If I try and point to memory address which hasn't been allocated, yes, you will crash the program just as if you tried to read memory that you weren't allocated ever. Yeah. Okay, Brown has answered. But yeah, arrays are actually pretty much pointers in C. Yeah, okay. All right, let's go back to the slides. That's a bit too much talking. Well, not really. So this is how we create pointers, which we've just had a look at. So let's visualize this a little bit. So if I create... Okay, this is a really cool little demo here. So I create a pointer to an integer. So I go int asterisk number. So my variable name is number, and it's storing the address to an integer. The operating system gives us back some memory address. 1231, like it doesn't really matter. And this integer is being stored at the position 17. You can imagine like I can put in this memory address the value of the address of another variable, and I can now point to that variable. And this is why they're actually called pointers. And so in order to do this, we need this other tool, the address of operator, which we already introduced. So if we want to query what the address of a variable actually is, we can use the ampersand before the name of the variable. So that's the address of operator, and it's just the ampersand. So in this case, when I create a normal variable or any variable, like an integer called number, I use ampersand here, and I get back the address of the variable that's been created. Oh, you can't really see that image, but okay, yeah, this is the really cool part, and I'll jump into a demo to do this. This is why they're called pointers. So in this example, I create a variable called number. It's an integer. It's assigned the value of 2. This is a normal integer, right? Down here, I'm creating a pointer because there's an asterisk. And I say, hey, I want you to be assigned the value of the address of number. So if you have a look at our diagram, which is unfortunately a little bit small, what if I do that? Just for now. Nice. So here's this number. It's got the value 2, and it's got the memory address, let's just call it 3 for now, it doesn't really matter. Here's pointer to number, that's this memory address. It's got the address 14. And I actually assign it the address of number, which is the address was 3. So the address of 3 is the value. And now this pointer variable points to this number. Right? There's a line between the two. We can actually point to it. Yeah, you should have still... Sorry, there should be a semicolon there. Yeah, that's right. Okay, let's jump into code once I fix up this... Shrek, again, another good question. Why do we have to specify the type we're pointing to? Would the address change? The address does not change. It doesn't care about the address. The answer to your question is literally the next slide. So let's hold tight, but come back. Let's come back to it. I just want to show this demo. So let's go back to my code here. Yep. let's make this a bit smaller. So I've got this integer I. I've got, I'm printing the value out of it. I'm printing the address of it here. Okay, that's all about I. What I can do, let's not call it I, let's call it, you know, let's call it age. All right, let's call it age. So I've got this variable called age. Its value is 50. I can print out Ooh, whoopsie. I can print out its value and I can print out its address. All right. What I'm going to do here is create another variable, age pointer. It's a pointer. And I'm going to assign it. All right. This is the key. I want you to understand this. I'm going to assign it, not age. I can't do that. Why can't I do this, guys? Why can't I do this? I want my age pointer to point to age. Why? But why can't I do it like this? Yeah, that's exactly right, Lemon. That's not the address. That's the value. Like if I ran this program, I don't even know what it would do. That's exactly right. Like I'm surprised it's even letting me compile this. It might actually give me a warning. I'm hoping it gives me an error. Yeah. So it's saying here, like, this is not really compatible. You're trying to turn an integer to a pointer. Right? That's a great example. Remember, we've got this DCC help tool. If you ever want like an explanation or you know, just a second go at attempting it. You know, you're getting a warning from the compiler because of this particular line. You know, we create this pointer, and you're telling to compile hold a memory address, but it points to an integer. Okay, this is not actually a great explanation, but you get the idea. Yeah, well, we all need our AI help sometimes. So this doesn't make sense. So what do I want to do is actually point to where age is. So again, how do I do that? Tell me how I do that. I don't want to get the value of age. I want to get the address of. If only we had an address of operator, which we do. When we place the ampersand before a variable, we get the address of it, not the value. Okay? This is amazing. We get the address of age, we assign it to the pointer. This won't complain if I compile this. This will compile without a problem. This is just saying I'm not using it. That's fine. But there was no problem with that assignment. Okay? That's really cool. So we've got addresses and values, and we can get the address or we can get the value. And we can put addresses in address variables or pointers. Right? You can see where pointers do get a bit complex because there's just a lot of arrows and pointing and things. All right, there's one more missing step to this perfect. What's the word for a trifecta but with four things? Quadrifecta? I don't know what the answer is. All right, can anyone tell me? What do you think? So we can go from values to. We can store values. We can go from values to addresses, right? We can convert from addresses. You know, we can get the address of something, but what's missing? It's like right here. What might we want to be able to do? Very good, Farhan. Very good. Very good, Wantha. Very good. Yeah. You guys are great. You guys are you're on fire today. What happened? It's the storm. How do I get the value of this age pointer, right? Because if I just print age pointer, right? Like what's going to print? Whoops, don't do that. Like it's actually it's trying to print the like it just doesn't work. Like it's taking the address and trying to print it's trying to print the value. Like I want to print the value. Like how do I print the value? Right? Like, or is it possible? I mean, you know, the answer is absolutely. And so this topic is called dereferencing. Dereferencing. A pointer is sometimes called a memory address, is sometimes called a reference, right? It's a reference to another piece of memory. And the opposite of what we're trying to do is to dereference, okay? It's simply accessing the value at the address of a pointer. Really, it's accessing the value of an address, period. It doesn't matter if it's actually from... I guess it does need to be a pointer, actually, because it needs to be a variable. Okay, and this is the really... Like, I genuinely apologize for this, even though it wasn't my fault. But on behalf of software engineers, that especially ones that teach C and study C like you guys, I apologize for this. Because this is genuinely just annoying, and it doesn't have to be this way, but it is. The way to dereference is to also use the asterisk character. Why? I can't tell you. I don't know why they decided to reuse the characters for so many things, but they did. You'd think there was the great character shortage of the 1950s. I don't know what it is. So the asterisk symbol, when used with a variable name, not at a variable declaration, means to dereference it or get the value of it. Okay? Are we good with that? So if I go back to my code and I go back to my cheat sheet, I say the asterisk, when placed after a value, when placed before a variable, means dereference. Do you see the difference? So this asterisk is different from this one. This one is when we're creating a variable. You know what I should do? I should give an example, shouldn't I? Int x ampersand x means address of. Int asterisk x means pointer to an int. X pointer means dereference. Do we see that? Yeah, so when there's no data type, exactly right, Limes, when there's no data type on an existing variable of any type, the asterisk before the value means dereference it or get the value at that. Get the value, yeah. Okay. So, if we go here, how do I print the value? Can you guys tell me? What should I do? Well, it's not that. What should I do instead? Yeah, you guys, I'm genuinely impressed today. I just do that. Get the value stored at the memory address in the age pointer variable. Okay, let me say that one more time. Age pointer is a memory address. Dereference it. Right? Get the value at the address and print, and that should be a pointer because that should be an integer because it's an integer pointer. And so print a pointer. What should this print? What value should this print if this all worked and I didn't lie to you? What should we get here on this line? I'll put a new line here. Yeah, 50. Yeah, 50. Because why? 50 was stored here. And look at that. That's amazing. Okay, Bree or whoever's lecture modding. I know Bree's lecture modding. Could we do a poll to just do a check-in on this? If it helps, I can do a whiteboard of this program. So you let me know. Figma, that's what I was trying to remember. That's what I use for diagrams. Or I can make the poll. Let me know. Okay, I can make the poll. How do I make the poll? Start a poll. Oh, sorry. You've done it. So Lemon says, asterisk is used for both declaring a variable pointer and for accessing the value of a variable. Yeah, absolutely. Yep. Have a look at this file. Absolutely. These two things. So let's say you didn't put the asterisk. Would it have printed out the address again, or would you have to use Pete? So, I mean, we can, like, if you've got questions like this, these are good questions. The best thing to do is to test them. And the answer is, like, it's not quite clear. So, like, what it's trying to do, it's getting the address at age pointer, because that's what age pointer is. It stores an address. It's getting the address, and it's trying its best to convert that to an integer. And you can see it's not doing a very good job. And you can see how it's, because it's trying to convert that memory address into an integer. The other time I ran the program, I got a different memory address, so I got a different integer. So it's always going to be a different value. So the asterisk unpointers the pointer. Yeah. Well, we say dereference, but yes. Unpointers the pointer. I like it. So age pointer doesn't exist as a variable. Only age pointer does. No, Tadal or Tate. I don't know how to say your name, but age pointer is a variable. This is a variable. And it stores an address to an integer, or it just stores a memory address. But it is a variable. It's taking up memory. Why is this Figma not logging in? Open the app. Always open. All right. Do we want a diagram? So are age pointer and age pointer two different things? No, it's the same thing. There's one thing called age pointer. Okay. Age pointer. This is the only thing. It is a pointer to an int. It stores a memory. Okay, we want a diagram. I think we need a diagram. Give me a second. Oh my God. Sorry, it's making me pay. How do I not pay for a diagram? Anyone work at Figma can get me a free bloody license? Working. Give me a second. This will do. All right. Great. Screw you, Figma. How do I do this? Let's go to Chrome. Let's change this to Figma. Alrighty. Paint? I don't have Paint, guys. I'm on a Mac. Wake up. What are you guys talking about? Sorry, I'm joking. Alright. Here's my program. All right. I love Figma. Guys, tweet at Figma. Get Jake a free Figma license so he can teach his students how to code. We love Figma, and I absolutely love using it. But I'm poor and I got this free account. What can we do, Figma? All right. So here's a diagram. Okay, let's not get weird. I'm going to do a table. This is the way I like to think about things. Code Jake. I don't know what that means. You guys are... I don't know what just happened then. Everyone got strange. Use updog instead. Ben. What do you think I am? How many times around the sun? I invented updog. No, I'm kidding. All right, so let's pay attention here. Let's pay attention. Are we paying attention? Are we all paying attention? Let me move this below my camera. All right. We're going to model. Okay, this is if you're learning programming and you're coming across a tricky problem, whiteboarding is the best thing to do. I do it all the time. Even today, if I'm writing programs, you know, I write a lot of web stuff. I write a lot of machine learning stuff. I write a lot of AI stuff. I do whiteboarding all the time. It's really, really important. Okay, let's have a look at what's happening here. First line of code. Int age is equal to 50. What does that mean? It means I've asked the operating system for 4 bytes of memory, 32 bits, to store an integer called 50. So I put the value 50. Can I do that? In my memory. I also want to do that. Cool. So I get 50. Now, the other thing to note is that every element has an address, right? I don't have a quick way to do this. Sorry about that. I'll stop soon, I promise. All right, let's stop there. So by default, my memory has these addresses. These aren't obviously real, but they it's waving. But they exist, and they'd be much more sort of like longer and stuff on a real environment. So the first line of code, I ask for a piece of memory to store the value 50. And so in this case, I just got this block here. Yeah? Are we happy so far? All right, great. Let's move on. We say printf, the age of 50 is 50. So if we have a little print section here, then we get, like, if I get my terminal, so the integer 50 will get printed out. Can I just put that here? Is that fine? What does Lime say? What? Can you highlight the code? I don't know how much it'll scale, but I can... Oh, God. I can try. I don't know if you can really see that. I'll try. I don't know. Can you read that? Maybe I can just do this. That might be enough anyway. All right. So how does it choose the location for 50? Oh, good question. It's random. It's random. We can't control it. The operating system decides. So that's why we don't know where things will be stored. That's why we need to check what the address actually is. But good question. It's not necessarily the next one. Like, there's a lot of behind the scenes optimization to determine where things go. It's not something we can control. Oh, I've missed that. Okay. So we've done this. That gets printed to the terminal. Let's delete the comments just to make this a bit easier for us to read. Yeah. Can I do like a background somehow? No. I guess I can. What is this doing? All right. That's what I tried to do. Yeah, maybe I am doing too much arts and crafts. Sorry. All right. So we've done that. We've printed this line. That's the 50 that gets printed here. All right. What's this doing? Age is stored at %p of ampersand age. Ampersand age, right, looks at what is going on? What is going on with my Figma? Is it not X to do an arrow? What is going on? Okay, I don't know why it doesn't like that. So let me draw a let me do this. I'm getting carried away, maybe. There we go. Why can't I just like let it free flow? Okay, well that's meant to point to ampersand age. Oh, that's pointing to ampersand age. There we go. Okay, so age is pointing to the address of 7. So when we print ampersand age, %p, that prints what? What's it going to print? You guys tell me. Yeah, that's exactly right. Very good. What's okay? I should be specific. Age is this. Age is stored at this. Right? That's what's getting printed. Yeah, very good. All right. New line. We're creating a new variable here. All right, called age pointer. So what does that mean? A new variable gets assigned. Let's make it blue. Apparently I need this. I don't know what the problem with that is. That's really annoying. Whatever. All right, I can also make that blue. So I create age pointer. It stores the address at age. Okay, so the address at age, well, we look, age is storing 50. The address is 007. So this will store 0x07. Do we see that? And then we print a integer, %d, the dereference of age pointer. This is the key. This is the key part. Okay. So first thing we do is we have to go to age pointer. Well, age pointer points here. So the value is 0.7. we dereference it. What that means is follow the address back and get the value. So we go to location 7, which is here. We follow it because why? Because this is pointing to this. The arrow is the wrong way around, but you get the idea. And then we get the value of it, and the value is 50. So the value of 50 gets printed out. Yeah, just like that. Right, so following these links is really important. Since the ampersand is before the age variable here, it's talking about the address, and since the address is before, it's talking about the reference to the memory of age. Yes, that's correct, Gunther, but it's not talking about the reference to the memory of age. It's dereferencing the address to follow it and get the value, which is 50. But yes, that's good. Good improvisation. Thank you very much. I usually am a bit better with Figma. I don't know what went wrong there, but I think you get the idea. It's obviously way easier to do this stuff on pen and paper. So if you're doing stuff with pointers and you're getting stuck especially, and definitely with what's coming in the course, this stuff is really important. Do whiteboarding. All right. Let's see if there's anything I want to cover before the lecture break. Yes, you get paper. You get scrap paper for the final exam. That's right, Calvin. This is another demo program, just like the one that we wrote together, that you can just use for your reference, and it's just doing the exact same stuff we've been doing, but it's got some comments and stuff. Maybe it'll help you. Yeah, maybe it'll help you. All right, let's take a break because we've gone quarter past. I will set a timer of 3 to 5 minutes. We'll do a Kahoot, and then we'll keep going. Let's do this. Oops. Okay, you guys are making good progress through assignment 1. That's good. All right. I'll give it a few more minutes. All right. While people are joining, is there a white space between the data type and the name of the pointer when declaring a pointer? Yes, absolutely. That's correct. Sage 4.2 is making me rewrite the whole thing. Yeah, that's kind of the point, usually, window. That's what we call BL, bad luck. Good job. Yeah, but I guess good job to, being up to 4.2. All right, we're good to go. Let's start this thing. Oh no, don't do that. All right, week 5, lecture 2. Let's do this. I've only got 4 or so questions. Multi-select. What is the exact output of this on line 7 when it runs? 0 means the number 0. Oh yeah, that we're just saying that's not an O, that's 0. Yeah, so if you said the null terminating character or 0, you'd be correct. I'm pretty sure you would typically see 0 printed out to be the null terminating character, but it's the null terminating character. When you specifically try to print it, I think it'll print out a 0, but it's actually worth testing. But it will try and print it. A lot of people said no visible character. Yeah, I think it's a non-renderable character, but I'm pretty sure it prints a 0. Just to tell you that it's tried to print the null terminating character. All right, question 2. Here we go, a pointer question. Is this a valid line of code? Int asterisk x equals 50 is assigned 50. Kahoots in the kitchen are becoming a common occurrence for me. Sounds like a album title or something. Yeah, false. Why is it not valid? Why is it not valid? I'll give people a second. Why is it not valid? Yeah, because when we have an asterisk, when we're creating a variable, it's saying that this should store a pointer, and then we're trying to assign it not an address, but an actual value. So this is invalid. Good pickup. All right, what will this program print? Ooh, can you manually type in an address? The problem is you don't know what the address should be. Is it possible? Yes, I think it's possible. If you happen to know what it should be and you typed it in, you could convert it to a pointer and assign it. I think it's possible. It'd be a great little experiment to write up yourself. Wow, dead even 27. So what's happening here? A is 5. We create a pointer that stores the address of A. Okay. We print a decimal integer. So we know we're printing an integer because we have %d. And we're printing the D reference of P, which means we follow A to 5 and we print 5. So it's absolutely 5 here. It's absolutely 5. If you've got 27, if you put blue, I want you to really be sure you understand what you got wrong because it's really important. Okay, so this is my little warning for those of you who clicked blue. All right, second last question. What is the output on line 6? I think it means on the printf, by the way, not line 8, the printf. I should quickly check what this is. B, C, D, E. Oh, this is a great one. Yeah, it's red. So not many of you got that. All right, this is a good one to break down. A, B, C, D, E is the string. The string can store 10 elements, okay? Size is 10. We change the index of 3 to be the index of 5. So 0, 1, 2, 3. D is going to change to be whatever is stored at the element 5. The element 5 is 0, 1, 2, 3, 4, 5, which means it's the null terminating character, which means D is replaced with the null terminating character, which means when you print this string, you print A, B, C. Because D is the null terminating character, and then you lose, and then you don't print E. So only A, B, C got printed out. We made the string shorter. Well, these timers are brutal. We didn't know you can read. Well, there you go. This question's so hard, you have a minute. So be careful what you wish for. Alman? I like the 2 answers. I like the 2 of you that just gave up and just typed. I should look at this. Ugh. Yeah, okay. Not too bad so far. Yeah. All right. Plus. Yeah, good job. Good job. I can explain that if we like. Do you want throwing the towel? Do we want me to explain this one? Or like I can explain how I sort of solved it in the minute. Can I zoom in here? No. All right, can you just see this? Include standard IO main. We have this string, and by the way, I didn't write these Kahoot questions. These were from last term, so I'm seeing these fresh. It's not like I wrote this. We create a string called dog ! Double quote. The double quote means there's a null terminating character. When we don't have a size for a static array, it means the size is set. So the size will be 1, 2, 3, 4, 5 characters. So I'm just like, I didn't do this, but you could just write down in a piece of paper 5 characters. Or there's like 5 boxes, 1, 2, 3, 4, 5. We loop here. Now, we did cover for loops yesterday a little bit, but this is just a while loop where the I is in the body. What this is doing is it's starting at index 0 and it's looping while the character in the string at the index. So it'll be 0, 1, 0, 1, 2, 3. So DOG exclamation mark null terminator. While it's not the null terminator. So it's looping through every character, DOG exclamation mark. And it adds 1 to I every time the loop ends. So this is just a while loop going through character by character where S of I is the character at that particular point in the loop. If that character, if the ASCII value of that character falls between lowercase a and z, and so this is a way to say, is the character a lowercase letter? Because on the ASCII table, it goes from A to Z, A to lowercase z incrementally. Does that make sense? So all this is saying is for every character in the string, if the character is a lowercase character, there's only one lowercase character, it's O. So we run this body once, and it's when we're at the O character. And you can see that it does a bit of funky mathematics here. And then what it does is it sets it to A, which means it sets it to the first lowercase character, which is A, and it adds its own position minus A plus 24 mod 26. To be honest, I didn't even bother calculating this. I knew that it wasn't going to be A, and I knew that it wasn't going to be O because we're taking A and we're adding something to it. And unless we're adding 0, it's going to change. And I know it has to be a lowercase because we're modding by 26, so it can never go over 26. So it's got to be D, lowercase something, G, exclamation mark. It can't be this, it can't be this, it can't be this, so it has to be yellow. And if you can do that in under a minute, you're in a pretty good spot. Can't you do ASCII commands in the terminal? Absolutely. You can type ASCII in the terminal and have a look to remind yourself. Don't know what the whole citrus thing is going on about. Thank you, Bree, for sorting that out. All right, who podiumed? Yesterday we had some online podiums come and collect their Pokemon cards. That was fun. So was that Agile Leopard, Wonder Ferret, I guess, and Winged Sloth. Congratulations. Bring a screenshot to the lecture next week and I'll give you a Pokemon card. Good stuff. All right. Ooh. I lost my stream deck. All right. You'll win one. You'll win one, I promise. You'll win one day. All right. I've got a few things on pointers I want to talk about for the last 20 minutes of the lecture. All right, Jake. Sydney's storming. You've gone on about pointers. I get it. So there's memory addresses, there's values. We can dereference, we can get addresses. But what's the point? Why are these things useful? Why do we bother teaching them? Anyone agree? Why are these useful? Why are they useful? Why are they useful? But Jake, why are they useful? There's lots of reasons they're useful, actually. There's many reasons. If you've written a language like Python, who's written a language like Python? Python, TypeScript, JavaScript, C#, Java, anything like that, any object-oriented based language. If you've used a language like that, everything is pointer-based. It's just happening for you. So it's a very important building block for modern programming languages. But there's reasons it's useful, as some of you are alluding to already. They're useful in C. So how do we modify a variable within a function? All right, what does this mean? When you pass a variable to a function, okay, we pass a copy of the value into the function, which means when we modify it, okay, we can't do anything with it, right? We know this about passing values. So this sometimes poses a problem. Sometimes we want to do something called in-place modification, in which you modify a variable that you've passed into a function within that function. Okay, that's very useful. And the way we do that in C is with pointers. So let's have a look at this example. I've got my main function here. I have an integer variable called x. I have this function called change value. Okay. And it doesn't accept an integer called x. It accepts the address of an integer called x, which means I can modify the variable x by dereferencing it and doing things to it. Okay. And what that means is that x will actually change down in main. Okay. This is not something we have been able to do until this moment. When I print x here, and I'm going to actually copy this into VS Code and show you this. When I print x here, whoa, what just happened? Have I done something wrong? No? Okay. When I print x here, it's going to change. It's going to be doubled. It was 5. I passed x into this function. It modified x. It doubled it, right? It times it by 2. And when I printed it back down in main, it was changed to 10. So how does this work? Well, because when you pass something to a function in C, you are still passing a copy. So this is kind of interesting. In fact, what we really should do is go back to Figma. Oops. Let's just make this a little box like that. X, oh, why is it so small? Is that the size I should be? Yeah, I guess that was my problem before, like I'm too zoomed in. All right. X is 5. In fact, let's do this. This is x. It's an address. And it's got the value 5, right? Over here. This is in main. This is change value. Okay. I create x here. I give it the value 5. I pass the address of x into love to know why it's doing that. Into the input, which means x over here is some other address, but it's getting past 41. Do we see that? So it's actually interesting. Like, we still make a copy of this value, just like we've always done. All right. But the problem, the really cool thing is that that copy is still the same address that points to the integer 5. Right? This is passing the copy in. This points to 5. So when we get the value of x and we double it and we assign it back to x, what we're doing is we follow the pointer. We double 5 to 10, and we assign it back at the value at 41. And so down here, 10 updated because I changed it in place. Okay, that was a better Figma round, huh? So as long as you've got the address and you own the address, like your program created it, you can manipulate it anywhere. It's really cool. So direct use of variable from another function, absolutely. So we don't have to reassign the variable, absolutely. It's actually gone in and changed it in that piece of memory. Yeah, it's really cool. It's really cool. It's great to get your head around. Is this the reason why this changes the variable globally? So if we're using the address to refer to the variable, this is not a global variable. So don't get the two things confused. Global variables are still bad. This is not a global variable. You're intentionally passing the address somewhere else, and that in that place you can follow the address and do something to the value. We'll talk about arrays later. Yeah. So if I go back to my slides, this is kind of a technically interesting thing that sometimes people call this pass by reference, and I call it pass by reference too. I think it's technically not pass by reference, it's pass reference by value, but don't worry too much about it. But the reason it's pass reference by value is actually the core foundation of C has not changed. When you pass something to a function, you pass a copy. It's just that we're passing a copy of the address. And so, like, again, the whiteboard is key here. Oh, yeah, that one doesn't work. The whiteboard is key here. We're passing a copy of 41. Like 41 is copied, but you know, I guess the point is like if I could somehow change the location of X, it wouldn't actually update over here. But anyway, that doesn't matter. When is it better to pass by reference instead of returning the value? You shouldn't do it unless you need to, and there's a few times you need to do it because all of this adds complexity, so it's not necessarily a nice thing to do. So times when you need to do it, okay. No, that wasn't a good answer. Let me give you a better answer. When should you do this? There's a few answers. Number one, so remember, who asked this? Usage Life. Unfortunately, usage students asked a good question. What did I say a few lectures ago that's expensive and we want to do as little as possible? Allocating memory. So allocating memory is complex and costly. And Wunther actually has exactly the right answer. So it's a performance problem. Copying a small integer is fantastically simple. It's small. Like small single memory allocations are fine. Imagine if this was a really big piece of data. Like imagine this was an entire bitmap full of values. Like it could be megabytes of data. When you pass it to a function, you have to copy it. Yeah. And if you copy something, that means you need another memory allocation. It means at that point in your program, you're storing that full bitmap twice because you passed a copy. That's really expensive and costly. Passing things by value, unless the value is very small, is very expensive. So if you pass a reference to it, you don't need to reallocate the entire bitmap. You just need to reallocate the address. So you go from having to allocate a megabyte image to just a 8-byte pointer, 32-bit pointer. Do you see how you could copy that megabyte image 50 times? The great thing about pass by reference is that you're not actually copying the data. You're copying the reference to it. It's so cheap and performant. Does that answer your question, Usage Life? All right. Yeah, so we can change things in place and main points to the updated value. We saw that. All right, this is the last, I think, thing I wanted to talk about today. This is really cool. If we remember back to when we passed our array in the Connect 4 program, we manipulated the array in the function and it changed it in main. And I didn't pass a pointer, right? Like, in fact, here's this code snippet. Like, let's put this into VS Code. This is a really, really mind-blowing part of component of C. When I learned this, I was like, that's crazy. This is really cool. So let's look at this program. I have a 5-element integer array, 1, 2, 3, 4, 5. I pass it to this function. It accepts the array and it accepts the size. It loops through over each element. Don't know why that's capital I. That's probably just a typo from the slides. Let's change that. There we go. Let's return 0. I'm probably missing something. Yeah, that's all I was missing. All right. So I fixed this program up. If I go, let's do this again. For int I equals 0. I is less than 5, I plus plus. And I printf %d \n, comma, data of I. My question to you all is, will this print the doubled values or will this print the undoubled values? I don't really mind if you get this question right or wrong. I just want to know what you think. Going by the logic of what we've been teaching, this should be undoubled, right? Like, we're not passing in a pointer, we're passing in a copy of the data. When we pass in a copy of the data, what we do here should only copy it in, manipulate it in the local copy, the local variable, and so this should be unchanged. But if we run this program, we will get 2, 4, 6, 8, 10 printed out. So it does double it. So Elman or Lemon is right. Arrays can be altered outside of main and remain altered. The answer is yes, but why? Why, Lemon? Before you celebrate with a sleigh, why? Can you tell me why? It uses pointers, sort of, because arrays are amazing. I'm going to take that as an I don't know. Yeah, arrays are pointers, sort of. We have a term for this. They decay to pointers. They decay to pointers. What that means is when you create an array, what all you're really doing is asking for a memory address, a memory location which contains the first element. So if I have a 5-element integer array starting at the value 1, all I get back is I get back a memory address. Arrays are memory addresses, sort of. There's an asterisk. And because this is why arrays are so important. They're contiguous. It's why I kept going on about this so much. It's because when I have an array, all I do is I have the memory address of the first location in memory. This is like so cool, I think. Here's an array. It's got 1, 2, 3, 4, 5 in it. So it's a 5-element integer array. Yeah. What is my data? What is it? What actually is this thing? I'm just reading the chat. So Shrek's got it. Liam sort of got it. You guys have got it. It's not a secret. No. Whale doesn't have it. Ferran doesn't have it. So it's not a sequence of pointers. It's not a sequence of pointers. What is my data? It's integer sorting. Yeah, that's what an array is. But what is my data right here? It's a single pointer to the first element. That's exactly right. That's what it is. It's this. That's all an array is. Okay, here's the really cool thing. So if array is a memory address, how does this work? When we access elements, we use an index, but what's happening here? Yes, we go to the address of 2, but how? How? You guys are right. Thomas, you're right. It accesses the next element, but how? It's not passing anything by reference. There's no passing here. It slides what across, but what is a slide? It's contiguous. We go to the next one. But how? Okay, capture, got it. Capture, this is the first time I've ever seen you type a comment. We got a quiet study here. So we can do pointer arithmetic. What this actually is to say add, it's actually 8, I think. 8 bytes because I'm on a 32-bit machine. Sorry, 64-bit machine. It's actually 1 times the size of a pointer, I believe. This is what's actually happening. And we can actually test this in code. But we can actually just add the size of the memory address, right? The size of this block, and that's how we move over. Okay, if I'm fast enough, we can do this quickly in a program. So let's try this here. Printf. I want to show you something first. %p, let's see how good I am. My double array of ints. Oh, sorry, no, data. Look at that. Data is a memory address. Data is a memory address, right? That means while I can do this to get the first element, I can dereference it. Because when I dereference, I follow a memory address and I print the value. Let me just put in some \n's. It is just a memory address. Do you see that? I mean, isn't that amazing? And then I can say data of 2 is this. Sorry, that should be 0. And data of this, now this part I might forget, but I can add, can I just add 2? I always forget. Let me try this. It might not work. Bree might need to help me out. It might be what I had in the oh no, that worked, but that just needs to be 1 here, not 2. That worked. Oh no. Sorry, and that needs to be 1 there, and that needs to be 1 there. Let me recompile that. Okay, that's not right. Data of 1 is 4. Yeah, so it's not right. It's not right. I think I need to do plus the size of a void pointer times 1. I guess I can do that. Data plus that. No, that doesn't work. Let's try it. That's definitely not right. Let me check this in a second. Yeah. You won't need to do this. I'm just showing you how it works. Pretty sure it accessed the first element of the array of index 0. Yeah, give me a sec here. I'm trying to show that you... Oh yeah, I just got this wrong. Whoops, I just checked it. I think you do this. I was just indexing it in the... that was the problem. I think it was just brackets. There we go, cool. So you take the memory address, you add the number of bytes, and then you dereference it. The problem is I was dereferencing it too early because the order was wrong. So if this was 2, it would be like this. Yeah, I was close there. It just needs to be like that. There we go, and we get the 6. So my point here is that these two things are exactly the same. So arrays sort of aren't really anything real. They are just memory addresses. How do you do that thing where you select all the ones and change them to a 0? So people ask me this all the time. In VS Code, if you select something, you see how the other occurrences show up. If you hit Command D, it selects the next occurrence. If you do that as well, I think you can do Command Shift L. That selects all occurrences, and then you can do multi-cursor editing. It's very useful, but just a little productivity thing. All right. Whew, what a lecture. Okay, please. There's a lot that goes into that lecture, so I would love your feedback. While I leave this up, I'm going to ask the questions. What if you're not on a Mac? Oh, it's just like Control or whatever the Windows shortcuts are. You can Google that. So data plus 0 is equal data of 0. First element from an array. Absolutely, animation. That's it. You got it. Would one be faster than the other? No, they're synonymous. This is, again, syntactical sugar. They are the same thing. Feedback form there. Thank you, Bree. So we could use a pointer to change the variable values however much we want, as long as it isn't part of an array. No, you could even do it in an array. You could even do it in an array. Like, I can do this. I can manipulate it, and then I can reprint it. And you'll see element 2 gets changed to 50, 0, 1, 2. It's the same thing. Whatever you can do with bracket I, you can do with this. Isn't that cool? That's what they are. Arrays are just pointers. All right, it's 12:58. I hope you had fun. I hope pointers wasn't too scary. This might be a lecture that you want to watch a couple times just to get your head around it. We put the lecture chapters on so you can skip ahead to the right parts. We've even got that tool that you can ask us where the lecture's content is. Thank you all very much. Stay dry. It seems really stormy, and I'll see you next week. Oh, it's Flex Week next week. What? Oh my God, I forgot. Thanks, Bree. That's amazing. No classes next week. We'll see you in week 7. So you got plenty of time to follow up on pointers. See you all.